Here's a video to show some examples of some VBA and HTA programming that I've done. VBA programming is basically Excel macros, and it'll transfer into AutoCAD Inventor. AutoCAD Inventor will run it. SolidWorks, I believe, still supports it, and Revit. But anyway, what I'm going to show here with the VBA examples is within Excel and then within AutoCAD. And then I've got something called HTA, which is HTML programming. And it's something that if I bought a computer right off the shelf at the store and it had Windows on it and nothing else, I could write these programs, and I could also transfer them to that machine and they're run ready. So I can email them to people. They don't need to know how to install them like you do with VBA. Or you don't need to have a secondary program to run the VBA code. You can just run HTAs directly from a Windows platform. And they're pretty efficient. You just need to know the language, because it doesn't help you graphically very well. You need to just know the programming lingo itself. But anyway, I'll just get started here. And what I have here, my first program, all these programs are basically analysis programs, because this computer that I'm using as an example isn't on a network. It doesn't have project files or anything on it. So these are more analytical programs, where if I was on a network, I've done programming for scheduling, consolidating data between different projects and giving real-time reports. But these will be more analysis-based. So I'll get started with this first one. It's called Roof Factors. And this program here is basically the first program I ever wrote professionally, I guess, as far as a work assist. And it was in the late 80s. I had a Commodore 64, and I knew QBasic. And so I wrote a roof factors program for combination roofs. And what a combination roof is it's a roof like the houses we did here in Omaha. Most of them are mid-range to upper end. So they would have one roof pitch on the front and back, and then the sides would be something different. So you might have like a 612 on the front and back, 1212 on the sides. A common roof is where all the roof pitches are the same, and you'll typically see that on 70s style ranches, split entries, things like that. They typically have a 412 to a 512 pitch. But this, basically, back in the day, back in the late 80s, we didn't really have anything that gave us what the combination factors were. For a common roof, a roof framing square has those numbers on it. So if I type in like 5 for a 512, I'll give it a hip width of 1.5 inches, because that sets this hip drop right here. This is a common roof. So if I had a framing square, most of these numbers would be on there. I'm not sure about the 44.31. If it gives you a sheathing factor, I don't remember that. I think a framing square gives you this. I don't think it gives you a hip drop, because hip drop is based on the width of the hip. So that's what you'd have on a framing square. But if I had a job that was like a 612, and let's say it's a 1012, I need to have custom factors for that. So it gives me all these different factors to figure out the roof. And so this started back in the late 80s. I wrote it on a Commodore 64 using QBasic. And then as my computer abilities and computer exposure went, I saw Excel, when I worked for an architecture firm. VBA is what Excel uses, which is basically QBasic. QBasic is pretty close to the same lingo. It uses for next loops, do while loops. It's kind of the same lingo. And so I wrote it in Excel, and then this is that version. There's an export factors button. You can just click, and it'll export it to Notepad, and this could be printed out and taken to the field. It's got a README button. It'll export, so it'll tell you what each of these, what the data means. What the sheathing factor is. It's the difference between the long point and short point of the sheathing along a hip. So when you're cutting sheathing for a roof, if the guy up on the roof gives you a dimension of 72 inches, well, let's use this as an example. Let's say he got the dimension on a 612 face and the long point was 75 3/4 inches. I would know that the short point was 50 inches, because I know it would be 25.75 inches shorter, basically, across the 4-foot width of a sheet. And so this is really helpful with kind of upper-end housing. And so I've got that in Excel. And then I can go over here to AutoCAD. And basically that same program will transfer right over to here. And so I've got the same thing within AutoCAD. I can type in a roof pitch, and if I'm working within AutoCAD trying to do 3D drafting or something, and I need to know rafter pitches or what the length of a hip is going to be, I can just figure it from this. So it'll figure all that out. So that'd be the common. And then this right here is the same as what Excel does. It just gives you the same thing. It says the same README file and everything. So that's roof factors in a VBA programming set. Then I've got something called HTAs. So I have this palette right here. So I just hit roof pitch. And I come in here and I hit 5. And it gives me, for the common roof, if I want to make it a 6, and this thing's set up so it takes that, whoops, that's not what I want. Let's fix that real quick. So it gives me this, and then I can just export it the same way. So it gives me the README and the export factors, and this is just through Notepad. So if I go down here to the file, I've got an HTA files. It's just this roof pitch HTA. It's 41 kilobytes. So if I wanted to just send that to somebody through an email, I could send it to them. It's run ready. They have Windows. They click on that. It'll run. It'll do exactly what it's doing here. So it's really efficient. It doesn't take any installation. And so I found that HTA is pretty good for like analysis type programs. If you're trying to do more graphical things, it's not great. It gives you a good user interface. You can set up a pretty decent user interface for people to put in their data, but it's good for calculating. I've got another one here, I guess, while I'm in the HTA files here. I've got one called bend compensation, and this is for figuring out the bend radius on sheet steel, so you can figure out the flat pattern. A lot of people, they have, most places they'll have like a bend chart that goes with their folder. I kind of like, this right here is mathematical. It figures it out. So as long as you know what the inside radius is, what the dies might, whatever the dies on the folder provide for that inside radius. If for some reason you're going to work outside of that arena, like there's a different folder you're going to use temporarily, and you know the parameters, but you don't have the load, you don't have the bend charts, this just works a lot quicker for me. I mean, I can just look at this and I can generate data instantly. If I want a 60-degree angle, I can get that instantly. And so basically what it tells me, let's go back to a 90. So this bend compensation is twice the setback minus the bend allowance. This is the amount to subtract from the outside flange dimensions to get the flat pattern size. So for an angle that was like 2 by 2, the outside flange dimensions, this mold line, would be 2 plus 2. So it'd be 4 inches. Your flat pattern width that you would draw in AutoCAD or whatever nesting software you have would be 4 inches minus this 0.217. So it would basically be 3.78 inches wide. And I could draw that width in AutoCAD, 3.78, DXF it out, put it into a nesting software and have a laser cut it. And then when they took it over to the folder, they'd fold it and each leg should be 2 inches. So that's what this does. So like I said, that's the same thing. It's bend compensation. It's 11 kilobytes. I could send that to somebody and it's run ready. So here we have a uniform beam program. And what this does is it designs uniformly loaded steel beams using ASD, Allowable Stress Design, or LRFD. And this works good. It's just real quick as far as if you know the tributary width, the length, the dead load, live load. You put all that in and you can cycle through different beam depths to figure out what size you might need. You know, if you're doing, it works for design, or even if you're just trying to figure out just generally ballpark what beam size you're going to need. It'll give you a great answer up front. And I've used this for shop drawing checking. When I was a structural technician, I provided design support and oversight to junior engineers, and I always like to just know that when the shop drawings came through, I would do a secondary check just to make sure that the beams we were specifying were correct. I mean, just to make sure that they had applied the loads right and everything. And this was basically just a quick independent check. So if I'm checking shop drawings, and let's say I've got beams that are 10-foot tributary width, they're 30-foot long, I know the dead load is 75, I know the live load is 100, 50 KSI. This takes beam self-weight into thing too. And let's say I want to limit it to 240, live load deflection is L over 360, and it gives me the beam size. If I want to do it in LRFD, it comes down here, it gives me the load case and does exactly the same thing. It gives me the actual moment, and then it gives me the ultimate moment here, what the beam capacity is. It checks for shear, and it checks for moment, and then it checks deflection. And it gives you the controlling load case in LRFD. In ASD, it gives you the controlling equation for shear. I think a W24 by 55 will use a different equation. Yeah, because it's got a non-compact web. So the shear equation sometimes varies a little bit. I think between both LRFD and ASD. Or between, I think that it's just non-compact in both, but let me check here real quick. If on the W16, if it used equation F, yeah, it uses the same one. So ASD, it's non-compact. The W24 by 55 is a non-compact web for shear. But it's real quick. And then I can export the results. So I could print that out if I needed to, or copy it and paste it into something maybe and format it so it looks a little bit nicer. And I can hit a README and it'll tell me what everything, the input section, what each thing means. Garage public assembly indicates if occupancy is rated as garage or public assembly for LRFD only, affects live load reduction. So that's just a note on what that checkbox means. And then what the results are down here. And basically that program's right here. It's called Uniform Beam. It's 28 kilobytes by itself, and there's a HTA support files. There's one called WData and WShapes. So the WData has things in it like the plastic section modulus, the section modulus, a moment of inertia area, things like that of each of the sections. And that's built from the AISC site. They've got a downloadable Excel file that has all the W shapes in it. I think it's got all the steel shapes. I just take the W shapes and I run it through an Excel program that just takes out the data I want, puts it into a notepad file. It's linear, and when I run that uniform beam thing, it just brings all this data in, and that's how it does its design. So it's really efficient. I mean, these things are small, they don't take up much room, and they're quick. I mean, you can send that to somebody that's not really computer literate. Basically, the uniform beam file and these two files, tell them to put them all in the same folder, and it'll run it. And they can be designing steel beams by ASD or LRFD if they want. So let's see. Oops, I closed that. So let me go back. I'm going to open up one of these HTML files, or HTA files. So I'll come in here. I'll look at the uniform beam one. So basically, it's got three sections, and HTA does. So it's HTML, and then it has a head section up here. And I'll open this back up again. So the head section, basically what it does is it sets the rules for the actual window itself, the overall window. So up here in the, like in the banner in the top, it puts in an ID of uniform beam, or title of uniform beam. That's right here. So that's what that is. And then it goes through, and it doesn't have a scroll bar. I can't open up more than one instance. Border thin just means that I can't stretch this. It's fixed. I can move the window around, but it won't stretch. If I put thick, it would allow me to grab these. You get the little arrows, and it would allow me to extend that out. Show in taskbar just means it shows up down here. So I can right-click on that and close it or whatever I want to do. The maximize button is not activated, so if I click it, it won't do anything, and the minimize button is. And so I can click that, and it works. Then down here, there's a style section. It's actually 4 sections for this one. So you have a head section. Then within the head section, there's a style section if I want to border things off. So there's a geometry section, a loading section, a design section, which is this right here. It sets the height and width of that area. Tells it what the border style, what the background's going to be. It's white smoke, so it's kind of this kind of grayish color. It sets it in position, so it's left 170 pixels, and it's down from the top 10 pixels. And design buttons, the buttons is over here, and the results is over here. And so that's the head section. It's got the window settings, and then it's got the formatting for internal areas, basically. I can set up internal areas here or not. If I didn't put this in, it would just have this stuff willy-nilly through here. And so this allows better formatting for the user form. Then I can come down here, and then this is where the calculations occur. So script language, I designated as VB script. It could be Java, and I think there's a few other options. CSS, I think, is this up here, but I think you can use CSS down here too. I've always just used VB script. It's pretty close to VBA. There's some nuances between the two, but they're familiar enough that I can do the programming pretty quick. So right here it goes through all the calcs. This is the calculation section. And then when it gets done with that, let's see. Then we get down here. The script section's over right here. That's the backslash script. Just defines the fact that the script section is ended right there. And now I'm into the body section. And the body is how this area within the window is going to appear. So within the division ID geometry right here, I'm going to make the font Arial, the font size 3 pixels. I'm going to bold it, italicize it, and underline it. And then I'm going to write geometry. And that's right here. And then I'm going to reset the font size to 2 pixels. I'm going to put in a break line, so that's just a return. I'm going to get rid of the underline. That's what backslash U means, turn off underline. Backslash I means turn off italicize. Backslash B means turn off bold. And then I'm going to do a paragraph, which leaves it even further down. And then it's going to put in W shape. It's going to have a break. And then it's right underneath that. That break below it puts in a select button, which is just this pull down. And it just tells it you're going to put in the name of it is WT types, and then on click you're going to select the beam. So I click it, and it just, if this changes, it goes through a program that does the results down here if it has the data it needs to do an analysis. And then that's just the display portion. Results, buttons, design. It has a couple radio buttons in it. So the design area, that's just the formatting for this area right here. So that's how HTA is basically set up. It looks more complicated than it is. It goes pretty quick. Because a lot of times I can copy code from VBA, bring it in, and I can just transfer it to VB script and then just do the formatting outside of that. So that's pretty neat. I was excited when I found out about HTAs because they're so efficient. It just makes it a lot easier. And they're great for, like I said, analysis programs. Let's see, what else do we have in Excel? I'll go back here. Whoop. So here I've got an equivalent salary. This is a quick calculation. I've talked to people before, and they talk about paying somebody 20 to 22 to 23 hours, or dollars an hour. And they've got overtime and stuff. And they're always thinking in terms of they're paying the guy $45,000 a year. And I said, well, assume they're going to work 45 hours a week, let's say, and you're going to pay them $22 an hour. That's $54,000. So that's that program. So let's see, what do I have here? So that's that. I've got a center of gravity calculator. So I designed switchgear in the past, which is heavy electrical buildings, and we would design the sheet. They were sheet steel enclosures. So in Inventor, we would design them in Inventor. We could get the weight of the actual structure itself from Inventor and where the center of gravity was, but then the equipment that was inside we didn't have modeled necessarily. That would just be provided by a manufacturer, and we'd know its location within the building, but we would need to figure out center of gravity for the overall building with the equipment inside so that the guys in the field knew how to pick the building up, and we could give them preferred pick points as a result. So I'll put in a few here as an example. And so it would just give me it'll give you the overall weight and then the center of gravity for the building. So if this was like from the lower left corner on a plan, this would be the X direction, the Y direction which would be up on the sheet, and then the Z direction would be from the floor up. And then you hit export results and it'll export it to Excel and provide this right here. I've got the same thing in AutoCAD. So if I'm in AutoCAD working on a plan, I can just come in here and figure it out. It'll give me the same result, and then I can just pop it on the plan and I'm done. And if I want to, basically I can export the results, print them to a PDF and keep them in a file so I can show that that's what I calculated for the center of gravity in case anybody came back and asked. Let's see. I've got a concrete beam in here. Let's see. Concrete beam is a simple analysis program. Typically, I don't think this one, it's not set up to do T-beams, but it'll still work. So I had one that does T-beams. This one here is a little bit more simplistic. But let's say I had a 12 by 21. It's 24 inches deep, let's say, or 24, but I'll say that the D value is 21.5 to the center of the rebar. 4,000 PSI concrete, 60,000 PSI reinforcing steel. And so what it tells me is what the area range is for the bending reinforcing. And so like the minimum is 0.86, the maximum is 5.516. And so let's say I was going to throw 3 number 6s in there, or 4 number 6s, let's say. So that would be 0.88, 1.76, is that right? 1.76. That's pretty light, but we'll see. Tell me what the moment capacity is if I put 4 number 6s in there. Just real quick, if there's a geometric limitation on a beam, you know, for depth especially, you can kind of see what the width needs to be and type in some numbers and see what you can come up with for reinforcing to meet the design criteria. So that's what that does. Okay, now I've got a beam analysis program, which is for continuous beams that are statically indeterminate up to 3 degrees of indeterminacy. So this would be basically for designing concrete slabs or concrete beams because they can be poured monolithically. For steel and timber, typically they're statically determinate for just regular gravity beams, just from a constructability for a constructability purpose. Typically, I never went over 3 columns, so I didn't even have 1 degree. But if I did, you know, those are simple enough to do by hand. You can just do virtual work, and that's what this does. It does virtual work up to 3 degrees of indeterminacy. So what it figures, and I'll just put in 1 load. I can put up to 10 loads, and they can be a mix of uniform loads and point loads. So I have a 40-foot beam. It figures there's a simple support at the left-hand end and a simple support at the right-hand end. And then I can put in up to 3 interior supports. So I can put one at the center. I'll put one at 10 feet. And I can hit solve, and it will give me the results. So for this is 1 degree of indeterminacy. So these are the reactions here, and then I have a spreadsheet that it actually puts the same results right here. And all it's doing is, this is the unit deflection at the support. So for virtual work, I would remove the support at x1, put a unit load there, and this is that value. And then I would do the virtual deflections, which is the uniform load without the support at x1, what its deflection was. And then I take this number times that number, and I get this R1 value. And then it just does statics to figure out what the remaining end reactions are. So that's for 1 degree of indeterminacy. So let's say I do 2, solve that, and it'll fill it out. Now it does the inverse of a 2x2 matrix. A little more complicated. It does the inverse of a matrix, and then, so this is the deflections at point 1, at reaction 1, reaction 2, if a unit loads at 1, and then this is the deflection at 1 and 2 if there's a unit load at 20 feet, which would be the reaction at 2, or the support at 2. Then it inverts the matrix, which it doesn't use any of this matrix of minors. You have to start using that when you get up to a 3x3 and greater matrix. So it just inverts these. Comes up with the determinant, which is, I think, this times this minus that times that. And then it does the inverse. And takes the inverse times these numbers to get the reactions. So let's do a 3x3. And so now it fills everything out. And this is just kind of a visual way, even if there's a young engineer or even a student, they can see how structural analysis on indeterminacy works. You can start seeing the steps. So the 3rd degree of indeterminacy, once you get up to a 3rd degree, 4th degree, 5th degree, 6th degree, it's really intense for the matrix because the inverse and stuff, all the calculations adding up exponentially. But basically after a 3x3 matrix and above, the process is real similar. A 2x2 matrix is unique. to invert it, it's easier. It's pretty simple. You don't have to go through all these other steps. And then just a one number is just 1 over that number, basically. So it comes back and it gives me the reactions for a continuous beam up to 3 degrees of indeterminacy. So it would be just a simple check on a concrete beam or something to see what my reactions were. If I'm checking a model or something just to make sure that RISA or even a 3D model is giving me the reactions I think I should have on a single section or something. Or I can build a moment diagram from this too. I've got the loading. And I can do programming to do that too. This program here, this Excel program, just does the reactions. So that's that. Another thing that's kind of useful, I've got one here, is, let's see, I'm going to close this and close that. So basically, I'm going to open up this general macros file has a lot of these macros in it, so that's where they're all housed in this file. So if I go to the project, the VBA project, I've got all these forms, and I've got all these modules. And let's say I want to back these up. I've done some work, I want to back them up, or I want to export them so if this file gets corrupted, I can just import them again. So let's say I come in here, I want to export roof factors. I export the file. I've got to go find the directory where it's at. So on this computer, it's here, and then there's one called General Macros, and then I go to Modules. And so I would hit Save, and I would say yes. And then I would go down here and I would do the next one. And I would do this all by hand, and it would take forever, and you wouldn't back up as much because it's just a pain to do this. So there's a program in here, and so let me go in here and General Macros. So here's where it is. It's got all the modules here, and all the forms, and all the class. I don't think I have any class modules in there. So let me just go back, and I'm going to delete it. It doesn't exist. So I got rid of all my backups. So I come up here and I go, here's my general macros. I want to export the modules. Whoops. So it goes through and it just exports them all. There's 94 different forms and modules in there, and it's done already. So I come in here, it made a general macros folder that I just deleted, and it redeveloped it all. At 6:44 p.m. on the 16th of November. So here they are. And so let's say I do some work, and I want to export these again. I just hit Export Modules, and it does it. It's got a user form, so I know it's working. So that saves a lot of time, and it makes it so that you back up more often so that you're not going to lose your work. Over here in AutoCAD, I've got the same thing. So let me go to it. And so I've got modules, and it's got 68 items. It's got 68 modules, and it's got 24 forms. So I'll come out here and I will delete these two. Whoops, I don't want to delete that one. So I'll delete those two. Continue. And so they're gone. So then I go up here to AutoCAD. This is AutoCAD 2002, and I just go to the Visual Basic Editor, and here's all the different forms and everything that I want to back up. So I come up here. I've got an EXM. I type that in. It's just a module I've written. I hit it, and it goes through, and there's 81 files that it transferred. And what it did is just rebuilt those folders again. So here they are. So it's real quick. Doesn't sound like much, but it's not having that. I mean, it's horrible to lose programming or not being able. If I need to transfer it to somebody or put it in a directory so I can just put it on a thumb drive or something, it's very quick. And so efficiencies like that. It transfers over even into production. Generating data, that's all this is. And so engineering and design and manufacturing are all data heavy. And if you can manipulate data and manage data, that's the whole key. It can make a difference between 6 weeks to a deadline or 6 days to a deadline. In some cases, it can make a huge difference. So there's just an example of some programming and a little explanation on HTA programming. So hopefully that was informative. Thanks.